we need to look at one more piece of the puzzle of galaxy evolution. We'll start with a bit of a detective story. In the 1960s, astronomers noticed objects in the sky that looked like stars, but had spectra that were completely different from any stars they'd seen before. Since the objects looked like stars, astronomers called them quasi-stellar objects, or just quasars for short. At first, they couldn't even recognize the spectral lines they were seeing. But eventually they realized that these were the hydrogen lines that had been redshifted further than anything else that had been seen at the time. The distances these redshifts implied were much larger than the distance to the farthest galaxies known at the time, several billion light-years away. As we saw earlier, we now have observations of galaxies that are further away than this, but in the 1960s this was far beyond anything known.
The fact that quasars looked like stars, even though they were billions of light-years away, meant that they had to be incredibly bright, brighter than most galaxies. They were also often seen as bright sources of radio waves, once again, much more luminous than most galaxies. However, there didn't seem to be any quasars close to us in space. The nearest one was 750 million light-years away, and most were much further. This suggested that these strange objects mainly existed in the early universe, and very few have survived up to the present. One last observation was even more puzzling. They could change their brightness dramatically in just months, or in some cases weeks. The reason this was surprising has to do with the limitations caused by the speed of light. For a large object like a galaxy, the overall brightness can't change in a time less than the time it takes for a beam of light to travel across it. For example, the Milky Way is about 100,000 light-years across, so it would take about 100,000 years for it to change its brightness substantially. However, if a quasar could change its brightness in just a few weeks, that suggested that it couldn't be much bigger than the solar system.
So here's the puzzle. Quasars were objects that were further away than anything else known, were brighter than entire galaxies, and not much bigger than the solar system. This is the kind of problem astronomers love to tackle. We've just looked at the connection between variability and the maximum possible size of an object. Now you should try explaining this in your own words. The best explanation here should also have a diagram.
Here's an opportunity to review the sorts of distance, velocity, and time calculations we did at the beginning of the term. If a quasar changes brightness in 1 week, what's the maximum size it could be? You'll have to calculate how far a beam of light can travel in 1 week. Make sure you give your answer in kilometers, then compare it to the sizes listed below. How many times larger or smaller is it than these sizes? At the same time that astronomers were puzzling over quasars, certain galaxies were also showing some surprising properties. They had large, hot jets of gas that could be seen at radio wavelengths. Often, these jets were much larger than the size of the galaxies themselves. In the picture on the right, the galaxy is the bright white area in the center, while the gas is the orange area around it. This is a false color image, so the gas is really glowing in the radio part of the spectrum. We wouldn't be able to see it in visible light. On the right, we can see huge red jets spread out around a galaxy. In the close-up, it's clear that the jets originate in the center or nucleus of the galaxy. Depending on the angle at which we see the galaxy, this nucleus can be much brighter than the jets coming from it. The gas and nucleus of the galaxy show up well in both radio and X-ray light. At the top, we can see Centaurus A in several different parts of the spectrum. The individual colors represent X-ray, visible, and 2 different parts of the radio spectrum. The top picture combines all 4 bands into one picture. The bright jets and extremely bright nuclei of these galaxies can make them up to 100 times brighter in the radio than in visible light. We call these active galactic nuclei, or AGNs.
In the 1980s, astronomers developed a model that can explain what's going on both with quasars and with active galactic nuclei. The model begins with the understanding that only one power source can generate enough energy in a small enough area to account for the observations of quasars, and that's dropping matter into a black hole. This may seem surprising. After all, when something enters a black hole, we lose all information about it except a very limited set of things like the mass. However, before it enters the event horizon, a mass falling into a black hole can release a tremendous amount of energy. This happens because the infalling matter doesn't just drop straight through the event horizon. Instead, it tends to form a disk orbiting around the black hole. Friction within this disk causes it to spiral towards the event horizon. However, friction in gas that is moving close to the speed of light will tend to make it extremely hot, many millions of kelvins, and this heat is then radiated out into the surrounding space. This is an amazingly efficient way to generate energy. Remember that in hydrogen fusion, only 0.7% of the mass is converted into energy. We can write this as 0.007 mc squared. In the disk surrounding a black hole, the amount of energy released can be up to half the mass energy of the gas falling in, or 0.5 mc squared. In other words, this can produce almost 100 times as much energy from the same amount of matter.
Of course, there's only so much matter that can squeeze into something as small as a black hole in any given second. If too much tries to fall in at once, the pressure of the light produced will push the gas back away from the event horizon. The only way around this is to make the black hole bigger. So, once the luminosity tells us how much gas is falling into a black hole, we can figure out the minimum mass for the black hole. Since quasars are more luminous than entire galaxies, the black holes have to be huge to support that. Estimates run from millions to billions of solar masses for quasars and active galactic nuclei. We call these supermassive black holes. When we look closely at even ordinary galaxies, we find that almost all large galaxies have supermassive black holes at their cores. We've already seen that our own Milky Way has one with over 4 million solar masses. We can tell this because we're seeing stars orbiting this massive black hole, as seen above. However, before you get the idea that all of the stars in a galaxy are orbiting a central black hole, remember that even a billion solar mass black hole is still tiny compared to the mass of a large galaxy like the Milky Way, with a couple of 100 billion stars. The other surprising thing about supermassive black holes is that they have very low density. Remember that the Schwarzschild radius of a black hole goes up with the mass. That means if you double the mass of a black hole, you double the radius. But the volume increases as the cube of the radius. So if you double the radius, the volume goes up 8 times. So volume grows much faster than mass. Since density is mass divided by volume, as the mass goes up, the volume goes up faster and the density goes down. A black hole with the mass of a star has to be denser than a neutron star. But a billion solar mass black hole has a density 100 times smaller than water. So if you bring a billion solar masses close enough together, it doesn't have to be compressed to high pressures to turn it into a supermassive black hole.
Let's summarize what this model predicts about the structure of a quasar. The heart of a quasar is a billion solar mass black hole with a massive disk of dust and gas surrounding it. This disk is several times the size of the solar system. This gas spirals in towards the black hole, orbiting ever faster as it gets close to the event horizon and eventually reaching a speed close to the speed of light. Friction in this disk heats the gas up to millions of Kelvin, causing it to glow brightly in X-rays. The energy of this hot gas, combined with magnetic fields connected to the disk, funnel much of the gas into twin jets emerging from either pole of the disk. These jets also move at close to light speed. The quasars that look most luminous to us are the ones that have one of these jets pointing right at us. A luminous quasar radiates 10 to the 40th joules of energy out into space each second, far more than the luminosity of even a large galaxy. To generate this much light, at least 17 solar masses of gas have to fall into the black hole every year. In other words, this black hole has to eat more than a sun's worth of gas every month.
So what's the connection between quasars and active galactic nuclei? An AGN is either a smaller version of a quasar or a quasar seen edge-on so that most of its light is blocked by the quasar disk. Either way, we can still see the jets of gas that have been blasted out of the center of the galaxy and extend out into intergalactic space. Notice that both AGNs and quasars require fuel to shine. If there isn't any gas being fed into the black hole, it'll stop glowing. It's likely that most or all of those ordinary galaxies we see around us were once AGNs or even quasars, since they all seem to have supermassive black holes in their cores. The black hole in the center of the Milky Way is too small to form a quasar, but it could have been a modest active galactic nucleus at some point in the galaxy's past. We see some evidence in the space around the Milky Way center that it may have produced jets of gas in the past. If something happens to dump more gas into the center of a galaxy, it can become active again. One way this can happen is if the galaxy collides with another one. Galaxy collisions usually disrupt the orbits of gas clouds in one or both galaxies, causing some of this gas to fall into the center and feed the black hole. This is almost certainly what happened in Centaurus A below, which is both an active galaxy and an example of a galaxy that has gone through a recent collision. Finally, this explains why there are very few quasars active today. Remember that galaxy collisions were much more common in the past when the universe was smaller and galaxies were closer together. Also, galaxies had more gas in the past than they do now. Both of these facts mean that the conditions needed to feed huge amounts of gas into a central black hole were much more likely to be met in the early universe. That's why we don't see quasars close to us today, though there are some active galaxies nearby.